Yeah, I think now we are on the live. We can start.
Okay, sir.
Dr. Ravi, please introduce Dr. Madhab Bera. Dr. Ravi, are you listening? Hello, Dr. Ravi. Dr. Ravi, please respond.
Hello.
Okay.
आवाज क्या है क्या अरे बोल रहा हूँ मैं कब से करो स्टार्ट करो हेलो
Hello.
Dr. Ravi, please start. Hello.
हेलो am I audible
Yes, yes, you are audible. Please start.
so good afternoon participants now we are going to start the second session of day 4 Dr. Madhab is going to present the session and before we start the session I would like to introduce about Dr. Madhab Bera sir Dr. Madhab Bera sir has received the Ph.D. degree from Indian Institute of Technology, Roorkee, in the field of polymer nanocomposites. He is expert in synthesis, modification, and characterization of graphene and related 2D materials. He has also gained experience in tailor-made synthesis of polyurethane and its nanocomposites for diverse applications. He has about 3 years of industrial experience, also where he was involved in the synthesis and application of polyester resin for coating and composite industries. Currently, he is working at Bhansali Engineering Polymer Limited. Here he is working on synthesis, modification and application of engineering plastics, their execution and injection modeling process, modeling defect analysis, etc. Some of the developments are development of different types of ABS engineering plastics, development of ABS polymer alloy with other engineering plastics, computing extraction and injection modeling of plastic. So without wasting much of the time, I would like to invite Dr. Madhav Bera. Sir, please come and give a talk, sir. Thank you very much, sir.
Thank you, Dr. Ravi. Can you listen?
Yes, sir.
Yes, yes, yes.
Audible,
You
sir.
are
Okay,
audible.
okay. Thank you for this nice introduction and good afternoon, everybody. Hope you all are fine in this pandemic situation, and also I welcome you to join and to for these presentations. And thank you entire NIT Jalandhar organizing team for this opportunity. So today my talk is on about the structure property relationship in graphene based polymer nanocomposites. So before starting the discussions, I would like to tell about the importance of this topic. So this structure property relationship is one of the most important and interesting topic in the field of polymer nanocomposites, because in today's emerging world, every engineering products has to meet certain criteria during their service, and if the material failure prematurely, then it will lead to a great deal of responsibility to the individuals who involved in design and development of that particular materials, especially in case of polymer nanocomposite. And it also leads to massive loss in terms of human cost, in terms of money. So without knowing the much insight about the structure, property, and their relationships, one engineer cannot simulate or cannot formulate proper material recipe. So in that aspect, it is a very important topic. So in my presentations, I would like to introduce about the nanomaterials, because I think most of the listeners or attendee are newcomers. So I would like to introduce about the nanomaterials, about the graphene, its development stages, and various graphene-based materials. And next step, I would like to introduce about the polymer nanocomposites. So in polymer nanocomposite, as you know, it is just like sea. It is a vast area because there are so many polymers and so many nanomaterials or micro materials that are reinforcing material that are available. So I would like to concentrate the presentation in terms of polyurethane and graphene nanocomposites. So polyurethane will be the matrix material and graphene will be the reinforcing materials. So the preparation method of this nanocomposites, and for the effective preparation and to get the maximum improvement, the surface modification of the nanomaterials is also required. That thing I will also discuss. And then how to make that nanocomposite, the various processes that will also cover, and then the structure property relationships, and finally the applications and summary. So nanomaterials, what is nanomaterial? We have heard this term so many times in our daily life, especially the researchers who are working in the material science or material engineering field. So nanomaterial is basically a material which has at least one dimension less than 100 nanometer. Okay, so here you can see pictorially, this is the diameter of our earth, that is 1.27 into 10 to the power 7 meter. This is diameter of football, that is 0.22 meter, and this is the diameter of fullerene, that is one dimensional nanomaterial, 0.71 into 10 to the power minus 9 meters. So from this figure you can just imagine how small this material is. So this nanomaterial can be of various categories. Okay, so it can be categorized into 0-dimensional nanomaterial, 1-dimensional nanomaterial, 2-dimension and 3-dimension. So if someone asks how we can say one material is 0-dimension, 1-dimension or 2-dimension, how we can tell about and how we can judge. So for this thing, we need to consider the international standard that is defined, that is assigned for this nanomaterial nomenclature. If a material is 1-dimension nanomaterial, that means only one dimension among the three is out of the nanometer range. For 2-dimension nanomaterial, only 2 dimension is outside the nanometer nano range, that is outside 100 nanometer. So definitely 1 dimension will be within the nanometer range. So for 0-dimension nanomaterial, like fullerene, the most example or most used materials, one of the, and for 1 dimension it is nanorod, nanowire, nanotubes like carbon nanotube, or you can say cellulose nanofiber, which is also another most widely research area. And for 2-dimension nanomaterial, that is nano sheet and nano thin film, also the graphene. And 3-dimension nanomaterial, nano cube and nano silica. So I would like to trace on the 2-dimension nanomaterial, which is graphene. So first of all, I would like to tell what is graphene and how it came into market. So graphene is a 2-dimension nanomaterial, as I already told. So it was first discovered in 2004 by 2 physicists, Andrew James and K.S. Novoselov, these 2 persons, and from Manchester University. And they actually, what they did, they simply used the Scotch tape that we usually use in our daily life, and they put the Scotch tape on the graphite surface, and they pull it, and then they pull the tape again and again, and finally they see the remaining material over the microscope, and they found very interesting material, and by this method they were first able to separate a single layer of graphene from the multi-layer precursor graphite. Okay, so it was discovered in 2004, and for this novel work they were awarded Nobel Prize in 2010. So graphene is one atom thick single layer graphite sheet, because the graphite is a multi-layered material, and if we can able to separate one single layer, that is the graphene. Okay, so in graphene every carbon atom is sp2 hybridized, and although we say graphene is single layered material, but as per the conventions, so the number of layers can be up to 10, and depending upon the number of layer, we designate them single layer, double layer, triple layer, or multi-layered. That I will discuss next slide. So the carbon atom in the graphene is arranged in two dimension like honeycomb structure. You can see here it's like a honeycomb structure, and it has unique combination of properties that is absent in most of the nanomaterials. So graphene is basically the basic structural unit for other carbon-based nanomaterials. So uh, if we stack the material one over another, then we will get the three-dimensional material graphite. If we wrap the material and then if we wrap the material, then we'll get zero dimension material, that is fullerene. And if we rolled it like a paper, if we roll a paper, it's like a paper. So if we rolled it, we'll get the carbon nanotubes. So that is a one dimension nanomaterial. So from this two dimension, we can go to one dimension, zero dimension, and three dimension. This is the beauty of this material. So as I told earlier, so depending upon the number of layers, we defined graphene into several other terminologies. Like if it is monolayer, then we called it pristine graphene or monolayer graphene. If the number of layer is 1 to 3, then we called it very few layer, and if it is 2 to 5, it is few layer graphene, and if it is 2 to 10, then it is multi-layered, and if it is more than 10, then we called it graphene nanoplatelet or graphite nanoplatelet. Now there are various ways to synthesize the two-dimension material, but the basic and most widely used methods that are mechanical exfoliation. Like if we put the material in some solvent like water or alcohol, and then we mechanically stir, or if we just sonicate the material, or if we just ball mill, okay, then we'll get the single layer graphene or maybe multi-layered graphene material. Then the reduction from graphene oxide. Graphene oxide can be reduced, and then we get the graphene material, and the chemical vapor deposition. And with this method, we actually get single layer and pristine graphene, but this method is very costly. Now, why people are talking about graphene and this graphene based material? Because it is the thinnest imaginable materials, having thickness of one atom, that is 0.34 nanometer. It is the strongest material in the world, with tensile strength 130 gigapascal, Young modulus 1 terapascal. It has exceptional electrical conductivity, around 7,200 Siemens per meter. It is the lightest charge carrier, zero rest mass, and record thermal conductivity 5,000 watt per meter per Kelvin. Very high specific surface area, 2,630 meters square per gram. Hence it is highly reactive. It is optically transparent up to 97%. It has antimicrobial property. It is ultra light material, and it has barrier property. So graphene has a unique combination of all these properties. So beside this, it has it has the property that it can kill the microbes also, like virus. So currently we are suffering from coronavirus. So people, researchers are trying to find out a way out from this coronavirus. And the researcher who are working in graphene field, they are also trying to utilize these materials for the treatment of coronavirus. So this is the basic structure of coronavirus, where the main responsible or main source of attack that happens through the spike protein. So this graphene based materials, it is used earlier already in some other research, not coronavirus, other virus research, that is herpes simplex virus type 1. So by using near infrared radiation and this graphene, researchers are able to disrupt the cell of this virus. So researchers are now trying to utilize this material for coronavirus treatment also. And with this graphene based material, we can prepare the face mask, we can prepare the drugs, and the in vivo treatment and air filtration also. So a lot of research is going on in these directions. Now, I would like to just tell about the graphene hype diagrams. So as I told earlier, first isolated in 2004, if you see the diagram, you can clearly understand. It was first isolated 2004, then its interest going on, and then people were trying to collab with the industrial person to prepare these materials, and finally the number of research and number of patents coming up to 2012 and up to 2013, because of lack of killer applications, then its interest is little bit fall, and slowly up to 2019. And after that, people found that the graphene based materials can be effectively utilized, although in many applications, but the most successfully and most viably it can be used as a reinforcing material or additive for rubber, plastic, and for paint applications. So full commercialization of this material is expected by 2030. Now, this graphene, although it has various merits, as I told earlier, in terms of mechanical property, electrical, thermal, optical property, antibacterial property, but the pristine graphene has certain demerits also. Due to its very high surface area, the material has inherent tendency of aggregations. So for polymer scientists, it is very difficult to disperse these materials because it easily gets aggregated. So due to hydrophobic nature of pristine graphene, it has limited miscibility with organic polymers and very challenged to disperse, and the pristine graphene is highly costly. So researchers were trying to find out some other way to utilize these materials. So the way out is the application of graphene based materials. So graphene based materials can be classified into mainly three categories: graphene oxide, reduced graphene oxide, and graphite nanoplatelet, or sometimes it is called graphite nanosheets, or some other terminologies are used. So graphene oxide, if you look at the structure of graphene oxide, then from the chemical structure itself, we can clearly see it has a lot of oxygen containing functional groups like hydroxyl, epoxy, carbonyl, etc. But if we look at the structure of reduced graphene oxide, then we can see it has very few remaining functionalities. And in case of graphite nanoplatelet, the number of layers is more than 10 that are stacked together, and we get the graphite nanoplatelet. So for thickness of graphene oxide single layer, it is around 1 nanometer plus minus 0.2, and for reduced graphene oxide it varies depending upon the degree of reductions. So it varies from 0.34 to 0.7, and for graphite nanoplatelet the thickness is around 3.5 to 100 nanometer. So here, few more graphene-based materials that are analogous to these three categories. Some of these three categories. So for graphene oxide, I told earlier also, it has a lot of oxygen-containing functional group, and the carbon-oxygen ratio. This is more deciding factor. That is around 2. But for reduced graphene oxide, it is more than 6. And for graphite nanoplatelet, less than 100. Graphene nanosheet, it is also like graphite nanoplatelet also. It diameter also less than 100 nanometer and sp2 hybridized, but it is in dispersed form. Okay. And graphene quantum dot, alternate graphene nanosheet or few layer graphene nanosheet, which is used particularly in the studies where photoluminescence is the target property. So for photoluminescence, we called it graphene quantum dot. Now, if we compare the properties of all these materials, then we can clearly see the surface area is maximum for graphene, and it has also maximum tensile strength, although graphite nanoplatelet has also similar tensile strength and modulus. But in terms of thermal conductivity and other properties, electrical conductivity, graphene is much higher. Now, if we compare these graphene-based materials or graphene material with other nanomaterial that are available, like carbon nanotube, if we see carbon nanotube with tensile strength is 660 to 150 gigapascal, whereas for graphene it is 130. Okay, and thermal conductivity is also higher, and for graphene electrical conductivity is also higher. And if we compare with polymer, so it is much away from this polymeric material, whether it is plastic, rubber or fiber. Now, if we look at this material over the microscope, electron microscope, then how it looks like. So this is the FECM image of graphene oxide, and reduced graphene oxide, this is graphite nanoplatelet. So from this FECM image, and this is these are the TEM image, so you can clearly see the size and thickness of this layers. So it is clearly seen that the graphene oxide layer size is much bigger compared to reduced graphene oxide. And if you look at graphite nanoplatelet, it is stacked like structure. So from the microscopic analysis, it is also proved the inner of this material. Now, if we do cross-section analysis of the atomic force microscopic image, then we can see the thickness of this material. So from the atomic force microscopic analysis, it is seen for graphene oxide thickness is around 1.4 or 1.5 nanometer, and for reduced graphene oxide it is around 0.86 nanometer. Now this graphene or graphene-based materials, because of their unique combination of properties, it can be utilized over a wide application area. So from this diagram, you can see it can be utilized over barrier application, plastics or polymer, structural applications, thermal management, aerospace, and blah blah. Lot of applications. And the most wide and most viable application is in composite materials. So you can see here the largest area that is covered, that is the composite sector. So in composites, before going to the composite or nano composite, I would like to tell about what is nano composite. So nano, as you know, the composite means, if you say composite, then mixture of one or two or more materials. So in case of nanocomposite is a high performance materials where the reinforcing phase has at least one dimension nanometer range, and it gives the enormous improvement in properties like mechanical, thermal, electricals, barrier, or other properties. So matrix and reinforcement altogether gives you the nanocomposites. So nanocomposite can be classified into three categories, mainly polymer nanocomposite, another one is metal matrix nanocomposite, and third one is ceramic matrix nanocomposite. So we are basically focusing on polymer nanocomposite. So why we do polymer nanocomposite? So we do polymer nanocomposite because of getting certain improvement compared to the base materials. So that improvement may be in terms of mechanical property, electrical, thermal, UV protection, longer wear, weight reduction, fire deterrence, barrier, flexibility, lot of properties can be improved by doing or by making the polymer nanocomposites. So in this presentation, I will try to cover most of these properties that is affected or that is improved with the incorporation of the 2D materials. So as you know, there are a lot of polymers. So I cannot cover all these polymers in a single presentation. So I will do on polyurethane and graphene based materials. So we can make, instead of polyurethane, we can make polymer nanocomposite by using polyvinyl alcohol, polyvinylidene fluoride, rubber, PET, epoxy resin, polystyrene, polylactic acid, and polycarbonate, and so on. So why I choose polyurethane? Because polyurethane has certain advantageous properties. Polyurethane is extremely versatile thermoplastic materials. It was first discovered by German scientist Otto Bera and his co-worker in 1937. So its property can be tailored, and I will show you how we can tailor the properties of these materials. It has very high elongation, tensile strength, abrasion resistance, tear resistance, chemical resistance. So polyurethane is also biocompatible too. If you look at the basic structure of polyurethane, so there are three main components. One is diisocyanate, another one is the polyol, and third one is the chain extender. Okay, so diisocyanate or polyisocyanate and this chain extender together, it will form the hard segment of this polyurethane, and the polyol, it will gives the soft segment. So in polyurethane, there is combination of hard and soft segment alternating. Okay, and because of this, it has flexibility as well as it has strength. And this hard segment is basically crystalline in nature, and it provides the strength, mechanical property to the material. And this soft segment, it is basically amorphous in nature, and it gives the flexibility and elasticity to the material. So for this polyurethane synthesis, as I told earlier, the basic material that are used, polyol, and I have shown here a list of polyols. It may be polyester based, polyether based, polyacrylate, etc. Diisocyanate, it may be MDI, TDI, or HDI, hexamethylene diisocyanate. So these are this may be aliphatic diisocyanate or aromatic diisocyanate. We have to choose this diisocyanate based on our requirement. And there are so many chain extenders. Okay, chain extender, the most widely used, that is the ethylene glycol. It is butanediol, that is most widely used. Instead of this, we can use hexanediol also. And catalyst, that can be used to accelerate the reaction, and dibutyl tin laurate, dilaurate, that is used mostly for the polyurethane synthesis. Now for polyurethane can be synthesized in two different approaches. One is one-step approach, another one is two-step approach. In one-step approach, what we do, we mix polyol, diisocyanate and chain extender, and then we stir the mixture in presence of heat, and ultimately we get the polyurethane. In second approach, what we do, we just make the pre-polymer. Okay, pre-polymer is made by reaction of diisocyanate and the polyol. So this pre-polymer is isocyanate terminated, as you can see here. Sorry, you can see here the isocyanate is at the end position. Okay, so this isocyanate is always remain free for reaction with further polyether or chain extender. So in the first step we do not add chain extender, we add polyether and polyol and the diisocyanate to get the pre-polymer. In the second step we add the chain extender, and this chain extender react with the isocyanate terminated polyurethane pre-polymer and will gives the final polyurethane materials. So the chain extender may be diol type or diamine type. If we use diol type chain extender, we will get polyurethane. If we use diamine type chain extender, we will get the polyurea. Okay. Now for the making of polymer nanocomposite, so it is various approaches there. So the most important thing is being a two-dimensional nanomaterial and being high surface area, graphene will try to aggregate. So we need to disperse this material before adding to the polymer or after adding to the polymer matrix. So the most convenient way is to disperse the material in a solvent or in a plasticizer before adding to the polymer. So there are various ways. First of all, we can functionalize this material. Second, we can mix with solvent or plasticizer, or we can disperse with some surfactant, and we can mix it with some and disperse it with some monomer also, and monomer or resin. Okay, and then we can polymerize this material, or in some cases we can just dry the mixture and we'll get the composite materials. So these are the various way to disperse the material. Now for the easy dispersion, we need to sometimes modify the surface of these graphene based materials, and this modification can be done by attaching small molecule or sometimes polymer chain. In case of small molecule attachment, we can attach various kind of amines like octadecyl amine, or we can attach some silane coupling agent. Okay, so as it is shown here, amine attachment. In case of polymer attachment, we can attach like polyvinyl alcohol or polyurethane. Here I have shown the attachment of polyurethane within the graphene oxide nanosheet. Now the next step is, after modification, after dispersion, the next step is to prepare the nanocomposite. This nanocomposite can be prepared by in situ polymerization, by solvent casting or solution polymerization, and by melt mixing approach. So in situ polymerization, what we do, we just mix the monomer, and we just mix the monomer and the initiator, and then we polymerize in presence of the polymerization conditions like heat or sometimes some other forms of energy that is required. In solution mixing, what we do in solution mixing, we first disperse the nanomaterials in some solvent, and then we separately prepare the solution of polymer also in same solvent, and then we mix the reinforcing material dispersion and the polymer solution together, and finally we heat up and then we remove the solvent to get the composite material. In melt mixing, what we do in melt mixing, we just put the nano reinforcing material to the polymer in melting conditions, and for this extruder or micro compounder that is used. Now after preparing the nano composite by various way, the deciding factor that govern the properties of this material, that is the morphology of this nanocomposite. And this nanocomposite morphology, it can be phase separated, it can be intercalated, or it can be exfoliated. So as a material scientist, our target is always to get exfoliated nanocomposite, as in case of exfoliations, the materials are the reinforcing filler or reinforcing material are uniformly dispersed throughout the matrix. And because of this uniform dispersion, we will get uniform properties as well as very high improvement in properties. So after getting the nanocomposite, the important thing is the what will be the final properties. So this is defined by its structure property relationship. Due to ultra thin cross sections and high surface area, graphene based nanomaterial can interact with the polymer at the molecular level, and depending on this degree of interactions, we can get various degree of improvement in properties. Okay, so now I will discuss about few of these properties that is improved with the incorporation of the graphene based materials. So this structure is related to property, and this property is ultimately the deciding factor of application or performance of the material. So the three things are interrelated to each other. First one is mechanical property. So to know about the mechanical property and its improvement, so it is very important to know what kind of interactions that happens within the polymer matrix. So the interactions can be covalent, it can be non-covalent like pi-pi interactions or electrostatic interaction, or it can be simply just blending. Okay, blending and or simply the dispersion. There is no interaction. So all possibilities are there. So depending upon the interactions, we'll get the improvement in properties. Now I will show the effect of number of layers of graphene on the mechanical properties of its nanocomposite. So from this diagram, you can see the effect of tensile strength with the number of layers. Not only tensile strength, the effect of Young modulus also. Okay, so the main outcome of this diagram is with increasing number of layers, okay, the modulus of the material increases. If you see the figure B, then you can clearly understood this thing. Now, if we add two different type of nanomaterial, one is graphene oxide, another one is reduced graphene oxide into the polyurethane matrix, then we will get different degree of improvement, because as I told and shown earlier, because of different degree of interactions between the polymer and filler. So with the incorporation of 0.1% GO, 280% improvement in tensile strength and 410% improvement in toughness observed. But if we incorporate similar amount of RGO, then we will find 245% improvement in tensile strength and 200% improvement in toughness. That means with the incorporation of GO or RGO to the polyurethane, it improves not only the tensile strength but also the toughness of the material. So this is the interactions. Now, if we modify the graphene oxide by using a different type of amine modifier like hexamethylene diamine, paraphenylene diamine, or ammonia, and then if we incorporate this amine modified graphene oxide to the same polyurethane matrix, then we can also find at
simple, but the measurement
hello,
very much complex, and due to the complex behavior of
hello.
Audible, sir. Audible, sir.
Hello.
Hello, sir.
Is
It's
there?
audible.
Okay, okay. So if we incorporate just 0.1%, I have fixed the filler percentage 0.1%, and then varied the amine modifier. Then you can see different degree of improvement. If we add GO, then it will be the tensile strength increases to 31 from 8.6 to 31.78, and for GOPPD it is goes up to 41.7. So you can see the effect of modification or effect of the structure of these graphene based materials on the properties like hardness, toughness, elongation, and the young modulus also. So 376% improvement with the incorporation of 0.1% GOPPD. Young modulus is improved up to 155%, and elongation 52%, and the sore hardness is improved 475%. Now this is the interactions and the chemical structure that is responsible for this kind of improvement. In case of GO, if we look at the structure here in number figure A, then you can see in case of graphene oxide, there is only one hydrogen bonding interactions with the adjacent urethane linkage. But if we use amine functionalized GO, then there will be bidentate hydrogen bonding interactions, and because of these bidentate hydrogen bonding interactions, the mechanical properties improve drastically. Now, if we modify the polymer structure itself, that means if we modify polyurethane to glycidol terminated, that is, if we incorporate some epoxy group into the polyurethane matrix, and then if we incorporate different loading of the amine functionalized graphene oxide, then we also find some different improvement in the properties. So tensile strength increases compared to the pristine graphene functionalized epoxy functionalized polyurethane to 123%, young modulus 158%, and elongation and break is also improving 27%. So this is the tensile strength variations with the incorporation of various different loading of graphene oxide, GOPPD, and this one GO. So if we compare with the thermoplastic polyurethane without any modification, and then epoxy modified graphene polyurethane, then we can clearly see the improvement in mechanical properties. Now, dynamic mechanical properties. So this dynamic mechanical properties actually very important for the use of this material over a long temperature range. So here we can see the dynamic mechanical properties of this material is affected very less if we go beyond the room temperature or beyond 0 degree. Okay, and because of this, the polyurethane nanocomposite material can be used in some environment where the temperature is below the room temperature. So the glass transition temperature of the soft segment is affected very less. In case of GO, it is affected 2 degree, but in case of RGO, it is affected only 1.7 degree, and the modulus is almost unchanged. So the material can be used for cryogenic applications also. And if we see the similar phenomenon for amine functionalized GO and the TPU nanocomposite, then we can see also the effect of the filler is very less in terms of the glass transition temperature. Although for amine functionalized GO, the effect is little bit significant, but for unmodified GO, that is only GO, the effect is very less. Now, the similar phenomenon is observed for glycidyl terminated polyurethane, that is epoxy modified, and the amine functionalized graphene oxide. The storage modulus increases with increasing GO-PPD loading, and the glass transition temperature also increases, but it is very less. So we can also neglect this improvement because it is only 1 or 2 degree improvement. So this is good for low temperature application of this material. Now, if we look at the thermal properties of this material, graphene-based polyurethane nanocomposite. So when we talk about the thermal properties, then it means the thermal stability and the thermal conductivity. So with the incorporation of graphene oxide and reduced graphene oxide, the thermal properties is also improving. With increasing with the incorporation of only 0.2% very ultra low loading, 0.2% RGO, the stability improves 6 degree, but in case of GO it is 10 degree centigrade. So this is due to the better interactions and better barrier of the material in terms of heat. Now for amine functionalized geo, that was without modification of geo. Now if we modify the geo with various amine modifier, then we also find that the thermal stability is increasing and the amount of improvement is much higher. So that means the structure is playing a role in improving the thermal stability of the material. And for epoxy modified geo, we can see the improvement is further increasing. Now if we look at the thermal conductivity of the functionalized graphene nanosheet filled polyurethane nanocomposite, so thermal conductivity is also increasing, and if we add 2% functionalized graphene nanosheet, thermal conductivity is increasing by 35%. So next is most important application properties, that is the electrical conductivity of the nanocomposite. So as the graphene has zero band gap, so zero band gap, we called it the zero band gap semiconductor, and because of that it has exceptionally high electrical conductivity, and this electrical conductivity can be utilized in various polymer nanocomposite. So the conductivity polyurethane, if we incorporate the material in the polyurethane matrix, then we can see up to 10 weight% loading. Okay, the properties, electrical conductivity is increasing very rapidly. Here we prepared the nanocomposite by two different approaches. One is electrospun, another one is the matrix material, another one is by casting the film. So there is significant increase in electrical conductivity of the electrospun mat compared to the casting film. So for high electrical conductivity, electrospun mat is beneficial. And then if we use the reduced graphene oxide for the similar type of matrix, thermoplastic polyurethane, then we can also see a lot of improvement in terms of DC conductivity. So the conductivity values is again related to the surface area of the functionalized graphene materials. So in this research, the BET surface, we utilize two different types of graphene based materials, one having the surface area 513 meters square per gram, another one is 765 meters square per gram. So what we found with the incorporation of 5.5 pHr functionalized graphene, the conductivity is increases from 1 into 10 to the power minus 11 to up to 1 into 10 to the power minus 1 Siemens per centimeter. So rapid improvement is observed, and the improvement is much more in case of the higher surface area graphene sheet. The another electrical property, that is the dielectric constant. So dielectric constant of thermoplastic polyurethane, that is also increasing with the increased loading of graphene nanosheet, and the effect can be found with varying the frequency. Okay, so dielectric constant increases with increasing the filler loading. So this means the capacitance of this material increases. So this material can be utilized in capacitance applications also. Now the surface property, when you talk about the surface property, that means we are talking about the contact angle that is created by using various liquid or various solvent. Most widely used liquid to check the surface property, that is whether a surface is hydrophilic or hydrophobic, is to check with water. So we can see with the now increasing number of layers, the contact angle is slowly decreasing. So the number of layers in graphene, that is the graphite nanoplatelet structure, is also a deciding factor in terms of the surface property of the nanocomposite. Now, here we incorporate two different types of nanomaterial. One is graphene oxide, another reduced graphene oxide, to check the hydrophilicity or hydrophobicity of polyurethane matrix. So we have found the thermoplastic polyurethane TPU nanocomposite, as we increase the loading, geoloading, the composite become increasingly hydrophilic. So this is due to the presence of the polar group within the graphene oxide nanosheet. And with increasing the loading of RGO, the composite becoming hydrophobic. So this is due to the hydrophobic nature of the reduced graphene oxide. Here you can see the contact angle at different loading of graphene oxide and reduced graphene oxide. Similar phenomenon is observed in case of amine functionalized graphene oxide. So if we modify the graphene oxide with amine modifier and then incorporate this amine modified graphene oxide into the polyurethane matrix, then we also find that with increasing the filler percentage, the contact angle that is increasing. This means with amine modification or during amine modification, the graphene oxide get reduced, and because of that, the material becoming hydrophobic. So this is the contact angle of various electrosperm materials. So here also we can find with increasing loading up to 2%, the water contact angle is increasing, and after that it is decreasing. That means the effect becoming less because of aggregation. Now, the next important property is flame retardancy. So, the flame retardancy of materials, also thermoplastic polyurethane, can also be improved with the incorporation of functionalized graphene sheet. Here, the lignin sulfonate functionalized graphene nanosheet was incorporated into the polyurethane matrix, and found that the total heat release rate, that is decreasing with increasing loading of functionalized graphene nanosheet. So by adding 2% functionalized graphene sheet, significant reduction, 62.8% in peak heat release rate and high char yield was observed. During the combustion, in situ formed char, that is derived from the catalyst action, that act as a barrier, and because of that it hinders the release of heat, and because of that heat release rate decreases. So in another work, Hu et al. They investigated the heat release rate with of water-based polyurethane by adding various weight percent loading of functionalized graphene. So release rate and total heat release density, it is also decreasing with the addition of up to 2% functional nanoseed, and it decreased up to 25%, but the smoke factor, that is also decreasing up to 38%. Now the next important properties, that is the barrier properties. So if you see only a single polymer matrix without any reinforcing filler, then the gas molecule can pass directly. But if we add two-dimensional nanofiller or any nanomaterials into the polymer matrix, then the passage of the gas molecules become very difficult, and they will try to pass and they will try to follow a tortuous path, and because of that the permeation of gas is getting delayed. In this work, the relative helium gas permeability of thermoplastic polyurethane has been investigated, and the exposure of helium gas is varied up to 200 hours, and found that the gas permeability getting decreases with increasing the exposure time also, and this is again similar due to the tortuous path that the gas molecule has to follow. So about 16% reduction in helium gas permeability observed with only 0.5% loading. Okay. However, with increasing graphene loading further, the trend of reduction of gas permeability is getting lower. In another work, Yusefi et al., they investigated the water vapor transmission rate of reduced graphene oxide filled thermoplastic polyurethane nanocomposite. So they found with the incorporation of 3 weight percent reduced graphene oxide, water vapor transmission rate of PU is getting decreased by 76%. So this barrier property in terms of water vapor transmission, in terms of gas, this are very important when we try to utilize these composite materials in certain coating applications. Okay. Now, next one is the corrosion resistance. This is the total scheme of the corrosion resistance, that is by barrier protection, cathodic protection, anodic protection, active protection, and self-healing. Okay. In case of polymer nanocomposite, the most widely used mechanism for the corrosion resistance is the barrier protections. So here, Lee et al., they investigated the barrier protections of graphene oxide and reduced graphene oxide filled polyurethane nanocomposite, and they investigated up to 235 hours, and their experimental data was also proved by dipping the material in 3.5% NaCl solutions. So in salt spray or in salt spray chamber, they found visually that the corrosion resistance is getting decreased in case of both GO and RGO, but the reduction is much prominent in case of 0.2% RGO filled polyurethane nanocomposite. So this corrosion resistance property is also very important for the coating applications. Now the antibacterial property. Antibacterial property is the ability of material to kill the bacteria. Okay, so in case of graphene based materials, the most widely used mechanism, that is the rupture of bacterial cell wall, as you can see from this figure. The rupture of bacterial cell wall by the sharp edge of the graphene sheet. So the antibacterial property is also dependent on the structure of these graphene based materials. Okay, for this is for graphite, graphite oxide, graphene oxide, and reduced graphene oxide. Antibacterial property of reduced graphene oxide is much more compared to the other because of its larger size. Now, Ann et al. They investigated the antibacterial property of PLA and thermoplastic polyurethane nanocomposite in gram-positive and gram-negative bacteria. So, after 4 hours of incubations, and they actually do two different experiment. They incubate up to 4 hours, and another one is 24 hours, and they found almost 100%. Okay, 100% reductions with the incorporation of 3 weight% graphene oxide reduces the growth of gram positive bacteria up to 99% and gram negative bacteria up to 100% at 200 hours. So the antibacterial properties of this nanocomposite is also found. Now, because of these various properties, this material can be utilized over a diversified area. So a few of these applications are in high performance composite materials, flexible electronic device, biomedical, and antibacterial and anti-corrosive coating applications, flame retardant materials, and supercapacitors also. Now, I would like to summarize the presentations. So, polymer nanocomposite based on graphene and graphene-based materials is one of the most promising and technologically promising development of 21st century, and its applications is ubiquitous. It can be found in biomedical field, it can be found aerospace, electrical applications, it can be found in coating applications everywhere. So to fulfill the diversified demand of modern technology, development of new materials having specific properties required, and for that detailed knowledge of this structure and properties is important, and variation of properties with number of layers, type of nanomaterials and their modifications, functionalizations, okay, is discussed in these presentations. And I hope this structure properties relationship and their correlations is very useful and can be utilized in any applications related to this field. So these are the following references that are utilized to prepare this manuscript, to prepare the presentation, sorry. And finally, I would like to thank you everybody for your kind attention, and you stay safe. Now you can ask if you have any questions.
Thank you, Dr. Madhab Bera, sir, for such an entertaining and enlightening presentation on the nanocomposites. Am I audible, sir?
Thank you, sir.
Yeah. It was very clean and...
Thank you, sir. Hello.
Yes, sir. Am I audible, sir?
Yes.
Yes, sir. It was very clean and detailed talk, sir. We are amazed to see such a mysterious area clarification. The audience must have gained immense knowledge by this
Thank
talk.
you, sir.
We from the organizer of CCTA 2020 owe you vote of thanks for being here even after your busy schedule. We really appreciate that. Please accept.
Okay. Thank you.
Before we wrap up the session, I would like to have some queries from the participants. So the first query:
Sure.
what are the easiest method of doping graphene?
Sorry.
What are the easiest method of
Can you repeat, please? Of doping?
Graphene.
Easiest method.
Yes, sir.
Okay. For doping, we can use this autoclave method. That is most easiest and most convenient.
Okay. What are the graphene applications at high temperature?
Graphene application, actually it is limited, not a very high temperature. pristine graphene can be utilized because it has no functional group and nothing to worry about the stability because of this carbon-carbon double bond structure. But in case of graphene oxide, as you know, there are so many oxygen-containing functional group, so there may be chances of the degradation of that functional group because of high temperature.
Okay. So the next query is, why the time ignition of a polymer composite reduced after addition of graphene?
Why?
Why the time to ignition
Sorry, sir.
of a polymer composite? Hello?
Hmm.
Yes, sir. Why the time to
Hello.
ignition
Yes.
of a polymer composite reduced after addition of graphene?
After addition of graphene material.
Yeah.
Okay. Okay, I understood. This is because of 2-3 factors. First of all, the graphene, it has very high barrier property. Okay, so because of that barrier property is restrict the heat as well as it restrict the passing of oxygen that is required, very much required for the burning of material. Okay, and another one factor is the very good interactions between the matrix and polymers, and because of that, it can act as a inherent part of the composite material.
Okay. Sir, the next query is, how to find BET surface area?
BET surface area can be found by nitrogen absorption technique.
Okay. 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 Sir, I don't know the last query whether it is relevant to your talk or not. Why the response time is greater than recovery time for certain material in humid sensors application?
Why the
Why the response time is greater than recovery time for certain materials in humid sensor application?
response time is better than recovery? No, no, sorry, I
This
cannot.
I think is not relevant from your area, sir.
No, sorry
Okay.
to
Okay.
say.
Okay, I will take other query. Why the time
Okay.
to ignition of a polymer composite reduced after addition of graphene? TTI time.
You just
Why
you,
the
you
time?
just ask this question, I think.
Okay, thank you very much, sir. So these are the only queries, sir. Thank you very much, sir.
Mm. Okay,
Okay,
okay.
sir. Thank you
Thank
very
you,
much.
sir. Thank you
Thank
for
you.
the entire team. Mm.
So
Okay.
thank you, participants. Again, tomorrow we will be available in the morning by 10:45 or 10:50. By that time, bye. Thank you.